Hello everyone, it's Clover from 19. Today is day 18 in my challenge today, and what I'm going to do is I'm gonna watch some rest of video, the previous section that I didn't watch yet, and then there's some programming assignments, so that's all for that I'm going to do today. Let's start.
all your parameters and reshape them into a giant vector theta. So what you should do is take W, which is a matrix, and reshape of time and help me find bugs in my implementations of backpropagation many times. Let's see how you could use it too to debug or to verify that your implementation of backprop is correct. So your neural network will have some set of parameters, W1, B1, and so on up to WLPL. So to implement gradient checking, the first thing you should do is take all your parameters and reshape them into a giant vector theta. So what you should do is take W, which is a matrix, and reshape it into a vector. Take all of these W's and reshape them into vectors, and then concatenate all of these things so that you have a giant vector theta, giant vector parameters theta. So instead of a cost function, J being a function of, the W's and B's, you would now have the cost function J being just a function of theta. Next, with W and B ordered the same way, you can also take dW1, dB1, and so on, and reshape them into big giant vector d theta of the same dimension as theta. Right, so same as before, reshape dw1 into a matrix, db1 is already a vector, reshape dwl, all the dw's, which are matrices. Remember, dw1 has the same dimension as w1, db1 has the same dimension as b1. So with the same sort of reshaping and concatenation operation, you can then reshape all of these derivatives into a giant vector d theta, which is the same dimension as theta. So the question is now, is d theta the gradient or the slope of the cost function j? So here's how you implement gradient checking. And often a j. So here's how you implement gradient checking, and often abbreviate gradient checking to grad check. So first remember that j is now a function of the giant parameter theta, right? So you can also expand this out to j is a function of theta 1, theta 2, theta 3, and so on, right? However, whatever is the dimension of this giant parameter vector theta. So to implement grad check, what you're going to do is implement a loop so that for each I, so for each component of theta, let's compute d theta approx I to be, and we're going to take a two-sided difference. We're going to take j of theta, theta 1, theta 2, up to theta I, and we're going to nudge theta I to add epsilon to this. So just, increase theta I by epsilon and keep everything else the same. And because it's taking a two-sided difference, we're going to do the same on the other side with theta I, but now minus epsilon. And then all of the other elements of theta are left alone. And then we'll take this and we'll divide it by 2 theta. And what we saw from the previous video is that this should be approximately equal to d theta I, which is supposed to be the partial derivative of j with respect to, I guess, theta I, if d theta I is, the derivative of the cost function j. So what you're going to do is you're going to compute this for every value of I, and at the end, you now end up with 2 vectors. You end up with this d theta approx, and this is going to be the same dimension as d theta, and both of these are in turn the same dimension as theta. And what you want to do is check if these vectors are approximately equal to each other. So in detail, well, how do you define whether or not two vectors are really reasonably close to each other? What I do is the following. I would compute the Euclidean distance between these two vectors, d theta approx minus d theta. So just the L2 norm of this. Notice there's no square on top. So this is the sum of squares of elements of the differences, and then you take a square root to actually get the Euclidean distance. And then just to normalize by the lengths of these vectors, I divide by d theta approx plus d theta. Just take the Euclidean lengths of these vectors. And the rho for the denominator is just in case any of these vectors are really small or really large, the denominator turns this formula into a ratio. So when you implement this in practice, I use epsilon equals maybe 10 to the minus 7, so 1e minus 7. And with this range of epsilon, if you find that this formula gives you a value like 10 to the minus 7 or smaller, then that's great. It means that your derivative approximation is very likely correct. This is just very small value. If it's maybe on the range of 10 to the minus 5, I would take a careful look. Maybe this is okay. But I might double check the components of this vector and make sure that none of the components are too large. And if some of the components of this difference are very large, then maybe you have a bug somewhere. And if this formula on the left is, on the order of 10 to the minus 3, then I would worry. I would be much more concerned that maybe there's a bug somewhere. But you should really be getting values much smaller than 10 to the minus 3. Oh, and if it's any bigger than 10 to the minus 3, then I would be quite concerned. I would seriously worry about whether or not there's a bug. And I would then, you should then look at the individual components of theta to see, if there's a specific value of I for which d theta approx I is very different from d theta I, and use that to try to track down whether or not some of your derivative computations might be incorrect. And after some amounts of debugging, if finally it ends up being this kind of very small value, then you probably have a correct implementation. So when implementing a neural network, what often happens is I'll implement forward prop, implement back prop, and then I might find that this grad check gives a relatively big value, and then I would suspect that it must be a bug. Go in, debug, 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 and after debugging for a while, if I find that it parses grad check with a small value, then you can be much more confident that it's then correct. So you now know how gradient checking works. This has helped me find lots of bugs in my implementations of neural nets, and I hope it'll help you too. In the next video, I want to share with you some tips or some notes on how to actually implement gradient checking. Let's go on to the next video. In the last video, you learned about gradient checking. In this video, I want to share with you some practical tips or some notes on how to actually go about implementing this for your neural network. First, don't use grad check in training, only to debug. So what I mean is that computing d theta approx I for all the values of I, this is a very slow computation. So to implement gradient descent, you should use backprop to compute d theta and just use backprop to compute the derivative. And it's only when you're debugging that you would compute this to make sure it's close to d theta. But once you've done that, then you would turn off the grad check and don't run this during every iteration of gradient descent because that's just much too slow. Second, if an algorithm fails grad check, look at the components, look at the individual components to try to identify the bug. So what I mean by that is if d theta approx is very far from d theta, what I would do is look at the different values of I to see which are the values of d theta approx that are really very different than the values of d theta. So for example, if you find that the values of theta or d theta, they're very far off, all correspond to dBl for some layer or for some layers, but the components for dW are quite close. Right? Remember, different components of theta correspond to different components of B and W. When you find this to be the case, then maybe you find that the bug is in how you're computing dB, the derivative with respect to parameters B. And similarly, vice versa. If you find that the values that are very far, the values from d theta approx that are very far from d theta, if you find that all those components came from dW or from dW in a certain layer, then that might help you hone in on the location of the bug. This doesn't always let you identify the bug right away, but sometimes it helps you give you some guesses about where to track down the bug. Next, when doing grad check, remember your regularization term if you're using regularization. So if your cost function is j of theta equals 1 over m sum of your losses and then plus this regularization term, right, sum of the L of WL Frobenius norm squared, then this is the definition of J. And you should have that d theta is gradient of J with respect to theta, including this regularization term. So just remember to include that term. Next, grad check doesn't work with dropout because in every iteration, dropout is randomly eliminating different subsets of the hidden units. There isn't a easy to compute cost function J that dropout is doing gradient descent on. It turns out that dropout can be viewed as optimizing some cost function J, but it's cost function J defined by summing over all exponentially large subsets of nodes that could eliminate in any iteration. So the cost function J is very difficult to compute, and you're just sampling the cost function every time you eliminate a different random subset of nodes when you use dropout. So it's difficult to use grad check to double check your computation with dropouts. So what I usually do is implement grad check without dropout. So if you want, you can set heap prop in dropout to be equal to 1.0 and then turn on dropout and hope that my implementation of dropout was correct. There are some other things you could do, like fix the pattern of nodes dropped and verify that grad check for that pattern of units killed off is correct. But in practice, I don't usually do that. So my recommendation is turn off dropout, use drag check to double check that your algorithm is at least correct without dropout, and then turn on dropout. Finally, this is a subtlety. It is not impossible, rarely happens, but it's not impossible that your implementation of gradient descent is correct when W and B are close to zero, so at random initialization, but that as you run gradient descent and W and B become bigger, maybe your implementation of backprop is correct only when W and B is close to zero, but it gets more inaccurate when W and B become large. So one thing you could do, I don't do this very often, but one thing you could do is run drag check at random initialization and then train the network for a while so that W and B have some time to wander away from zero, from your small random initial values, and then run drag check again after you've trained for some number of iterations. So that's it for gradient checking, and congratulations for coming to the end of this week's materials. In this week, you've learned about how to set up your train, depth, and test sets, how to analyze bias and variance, and what things to do if you have high bias versus high variance versus maybe high bias and high variance. You also saw how to apply different forms of regularization, like L2 regularization and dropout on your neural network. Saw some tricks for speeding up the training of your neural network, and then finally, gradient checking. So I think you've seen a lot in this week, and you get to exercise a lot of these ideas in this week's programming exercise. So best of luck with that, and I look forward to seeing you in the week 2 materials.
There is an error in my Coursera account so that I can't proceed any assignment right now. So unfortunately, I need to stop recording. And before I stop, I'm just going to recap first. Today, what I learned is about gradient checking. That because it is quite difficult to calculate every gradient effect propagation for every step. So instead of just calculating the exact gradient, we can just take an approximation for this. So our strategy is that using two-sided differences based on the epsilon, which is really small value around the our target. Our target is zeta, and the epsilon is surrounded by this range of around this zeta. And to gradient check, we first vectorize this um, huge parameter in here from layer 1 to L. We are going to vectorize these as a big vector which is equal to j zeta. And then we also take derivatives of parameter and reshape them into a big vector which is derivative theta. And then our question is that is d theta the gradient is d theta is the gradient of g j theta. And as I mentioned, we can take up derivatives of we can use approximation here, and we compared with the true value of the zeta I. And to determine that whether our approximation has right value or not, we can follow this Euclidean norm distance and by comparing it with epsilon. And this is particular tips on implementation. So this is the end of today's recording, and thanks for watching.